Okay, this meeting is being recorded. So we're very happy to have Sergei Gukov and tell us about the Equivariant Verlinde formula for Coulomb branches.
Well, thank you very much. Thank you, Sasha. Thanks everybody for joining in. I have to say this is my first seminar via Zoom. So I hope technology cooperates, and I apologize if there are hiccups because it's probably my fault. Of course, if you have any questions, feel free to ask. We don't have too many people, so it would be totally okay to turn it into some sort of discussion. Feel free to jump in with questions or comments. In fact, I'll stress several points that were or are still not clear to us, so I'll be happy to hear some feedback either during the seminar or even after. So let me now try to share the screen. Let's see how it works and if it works. So can you see it?
No, not yet.
Not yet. So let's do this. How about now?
Okay. Yeah.
Okay, good. So let's see, how does it work? I'll do the full screen mode. So what I'll try to talk about today is connection between geometry and algebra. So the main theme, so kind of big picture, which I'll try to refine as we go along, is we'll find or study some correspondence between geometry of certain manifolds or spaces. The spaces will be called X, and algebra. So on the algebraic side, we'll try to get structures or discuss structures closely related to modular tensor categories, so abbreviated as MTC. So if you're ever lost in the talk or at any slide, again, think about this big picture. So we should be discussing either one side, namely geometry of spaces X, or algebras or MTCs on the other side, ideally some correspondence between them. So then once you become more fluid in this going back and forth, the right thing to keep in mind is the question, for example, if we're discussing geometric side, to ask a question, okay, what is the algebraic side of this correspondence, or vice versa? If I present on some slide modular tensor category, the question would be, okay, what kind of geometry corresponds to this modular tensor category or related structure? On the geometric side, this will be geometries of Coulomb branches, and Coulomb branches has recently become fairly popular in mathematical physics and in representation theory. So I think in that sense, it fits reasonably well to subject matter of the seminar. And I'll try to structure this seminar in the following way. We'll spend at least half of the time on the motivation. So I won't tell you the actual problem that we're studying beyond what I just said in some sense, maybe until the middle, and solution of that problem will take the second half of the talk. But first part will be really broader survey explaining why we care, why somebody should care about this sort of correspondence, why somebody should expect this correspondence. Simplest motivation, kind of already from this sort of slide, is that these are rather different things that we're trying to relate. So on the one hand, it will involve some geometric structures. On the other hand, algebraic structures. Connection between algebra and geometry always is interesting. So that's one thing. So hopefully by understanding it better, we can learn more about Coulomb branches on the one side, which are examples of these spaces X, and it's not limited to just Coulomb branches. And we'll hopefully learn something that we don't fully understand yet about tensor categories and related questions on the algebraic side. Now I see that at least on my screen, something being cut. So maybe.
Yeah, it's cut here as well.
Okay, so let me try to minimize it and. Okay, so this is one of the technology glitches that I promised. So let's see if I can fix it easily. Do you see the full slides or?
Well, just the arrow between geometry and algebra.
Right, so let me try to go to the next slide. So for example, how much of this slide do you see now?
That was good.
Well, omega, omega j, omega k.
Yeah.
Oh, excellent. Okay, because that was cut out before. So yeah, sorry, I'm still learning, as you can see, in real time. Right, so if you want to study this correspondence between geometry and algebra on algebraic side, tensor categories, we can just say that this modular tensor categories, MTCs, will be labeled by X. So that's a slight refinement of it. So sometimes I may call it on the algebraic side MTC of X. And let me now explain a little bit more, or say more about each side separately. So on the geometry side, we'll be interested in hyperkähler spaces. So our X in this talk will always be hyperkähler. So it has 3 complex structures. In fact, the whole family can take any linear combination, but basic generators will be I, J, and K, obeying the usual quaternion relation, and 3 Kähler structures, omega I, omega J, omega K, corresponding to these complex structures. So later on, I'll try to explain that the most interesting part of the story, and that's what was the motivation for this work and seminar, and that's the main class of examples I want to focus on, is when X is non-compact. So X is always going to be hyperkähler, but it can be compact or non-compact. My most interest will be in cases when X is non-compact, and the reason is, again, will be explained later. So in that sense, geometry side is already almost done, because there is nothing more I want to say about it now. From now on, you can start thinking about favorite examples of your favorite examples of hyperkähler manifolds. So simplest example, if I want to consider non-compact ones beyond just flat quaternionic spaces, in low dimension would be, for example, T star of CP1. So this obviously belongs to a larger family, T star of CPN. So that's a nice hyperkähler manifold. Complete Calabi metric on it was found by Calabi. And this in turn belongs to a larger family of cotangent bundles to Grassmannians of little lower n dimensional planes and higher n dimensional spaces. Other examples of non-compact hyperkähler manifolds are Hilbert schemes of points on LE spaces, for example, here just on C2, that's also good enough. Then many such hyperkähler metrics that were found on the geometry side were found as spaces of solutions to some PDEs. So for instance, if you take Riemann surface C and choose group G, then you can study G Higgs bundles on this curve. So the moduli space of that will be infinite dimensional hyperkähler quotient, and famously through Hitchin has hyperkähler. It's non-compact, so it's a perfect, another example that we can keep in mind. Then if you move to PDEs on higher dimensions, there are various metrics, hyperkähler metrics on moduli spaces of monopoles. So for instance, there is Lee, Weinberg, V metric. There is Taubin-Calabi metric. So these are all high dimensional analogs of LE, LAF metrics. So LE is asymptotically locally flat, asymptotically locally Euclidean space. LAF stands for asymptotically locally flat. And then people just continued naturally with alphabet. So G follows after F, so they call it ALG. And there is actually ALH type of geometry. So these are all 4 real dimensional spaces. But what distinguishes E, F, G, H is behavior at infinity. So they have slightly different behavior at infinity. And my favorite example here is actually G star. So that's a very kind of exotic, interesting hypercalorimetric, which is close cousin of LE, LF, LG, and so on, that has very interesting growth. So constructing such spaces, studying their metrics, interplay between geometry and topology is a very rich area. So it has been very useful in geometry and in applications to mathematical physics. I already mentioned monopoles and some other PDEs. And for us, all these hypercalorimetrics will be just concrete examples that you can keep in mind. And what I would really love to ask is, okay, what kind of modular tensor category can I associate to ALG star space? Or if you love Hilbert schemes of points on C2, natural question would be, what kind of modular tensor category can I associate to this X? They're all perfectly good candidates. So that's just, again, for concreteness, a very specific list of examples, and we would like to address this question. I have to say from the start that I don't know how to do this in full generality, but we'll offer you an answer which works most of the time. And that's why it's kind of frontier of this development. I don't have a full answer. I would love to have a full answer, but there will be many cases where things work very well, and surprising tensor categories emerge just attached to each of these cases.
May I ask some very basic question? So what do you want from this tensor category? What properties do you require?
Yeah, I'm about to switch to describing MTC side. And like I say, I'll formulate the problem perhaps toward only middle of the talk. That will be very specific, but I'll try to motivate it in the next 10, 15 minutes. So yeah, ideally, I would like to have something which is as close to standard definition of modular tensor category as it can be. I'll explain that it cannot be exactly that, but I'll clarify that in a second. But first, I want to make sure that we are clear with the geometry side. So on the geometry side, the only data that we need is a hyperkähler manifold. So these are some examples. And it can be compact. In fact, the problem that I'm trying to pose will be much easier if it's compact. For example, we can take K3 surface, where we can replace this Hilbert scheme or its resolution, resolution of the symmetric product by symmetric product of K3s. That's also a nice hyperkähler manifold of any dimension that you may want to consider. But in that case, the problem actually will be easier, surprisingly. So for people who care about Coulomb branches are subset of hyperkähler manifolds. They're always non-compact. So for example, K3 or Hilbert scheme of K3 can never be a Coulomb branch. But the problem that I'm going to consider is still totally fine as far as considering even compact hyperkähler manifolds go. Okay, so following the question, let me move on to modular tensor category side. So modular tensor category is a loaded term, and it's a very rich subject. So formally, what it is a non-degenerate spherical braided fusion category. So it has a lot of adjectives, and each condition has a meaning. So here on the slide, I only illustrate that it's braided. So for mathematical physicists, such categories recently play a very important role in condensed matter applications, where you can think about the simple objects in a category as anyons, and braided is really braiding of anyons in a physical three-dimensional space. So that's basically what this picture illustrates. Right, so in fact, in this condensed matter applications, one of the most famous set of anyons is called Fibonacci anyons. At the level of modular tensor category, that's a rather simple category with two simple objects. One of them is identity, the other that you can call X, and X tensor X is some linear combination of identity and X. So that defines the tensor structure and so on. But what the slide also illustrates is that modular tensor category comes with very concrete numerical data. So if you fear categorical aspects or formal algebra, then the part modular in the name has to do with the fact that each category comes equipped with so-called modular data. Namely, it carries a representation, a projective representation of a modular group, SL2Z. So modular group is generated by two elements that are usually called S and T. And therefore, to describe this representation, what you have to do is to say, what are these elements and how they act on our, basically on simple objects in this category. So in this case, again, we have two simple objects, so matrices will be 2 by 2, and it's easy to check that this S and T satisfy the usual relations of S and T generators in SL2Z. And modular data, namely this S and T matrices, is a kind of structure that I'll be after. So one of the questions was, what do I want from this correspondence? One of the things I want is S and T matrices. Namely, I want to attach in this correspondence to hyperkähler manifold, compact or non-compact, a set of S and T matrices. So that would be ideal world. If I have that, I can be very happy, go grab a beer and celebrate. But so that's the goal. Part of the reason is that modular data, S and T matrices, describe modular tensor category pretty well. In fact, for a while, there was a conjecture or belief, I don't know which word is better, that modular data uniquely characterizes the modular tensor category. As I understand, that's no longer the case, but I can't even give you example off the top of my head of some MTC which is not fully characterized by modular data. Namely, two MTCs which have the same modular data, but they're actually different. Right. So as you can also see from this concrete example of this Fibonacci anyons or Fibonacci MTC, the values of S and T matrices are very special. So here they have to do with number field of order 5. So it's a cyclotomic field of order 5. So 5 is, of course, standard number for Fibonacci. But this brings another aspect into this game, namely in the world of modular tensor categories, there is an operation which in particular acts on these algebraic numbers that we see as entries of S and T matrices. It's called Galois action. And it relates quite different modular tensor categories. So you can basically act with a Galois group, in this case of Fibonacci anyons that I showed you. The Galois group is Z5. It's extension, Galois group of extension of Q by fifth root of unity over Q. So that's Z5 as a multiplicative group. And it acts on Fibonacci MTC, producing new MTCs out of it. So therefore, if I'm really after exploring this dictionary between geometry and MTC, natural question, which in fact I had when I was learning this Galois operations for the first time, was what is the geometry behind it? Or if you learn about this Galois action on MTCs, it's very magical actually. It's not clear, at least it was not entirely clear to me why it's working, how it's working. It would be good to have a very nice, simple, intuitive kind of idea how very different MTCs sometimes can be related by such Galois action. So this question we'll be able to answer pretty much in full. So, but that's again a good illustration of how you take some natural thing on one side and try to ask what it would look like on the other side of this potential correspondence. Now, we'll spend, I spent only 2 minutes on geometric side. So that's where we have hyperkähler manifold X, and that was easy. I'll spend a little bit more time on the algebra side. So in part because the structure here is very rich and I don't want to cut all corners. So I want to say a little bit more. So modular tensor categories, at least in formal traditional sense, they have very meaningful deep connections to topology on the one hand, via topological quantum field theories on three manifolds, and to vertex separator algebras, VOAs for short. So in part, in this vertex separator algebra world, these S&T matrices that I mentioned that contain modular data of MTC describe something extremely natural and useful. So let me try to go through this slide carefully and decode it. Namely, in the world of vertex algebra, you can consider, so VOA is an infinite dimensional algebra. It's huge. It's by itself an interesting subject and sometimes is not easy to study. But again, you can attach to it some concrete numerical data. For example, you can take various modules, representations, V lambda, say with highest weight lambda, and consider characters. In this case, there'll be Q-series expressions where you take a trace of over this representation of some variable Q, formal variable, to grading, which comes from the conformal vector in your definition of vertex algebra. So this Q-series expression will have a lot of interesting structure about vertex algebra encoded in it. In particular, you can ask how it transforms under modular group SL2Z, which acts on tau in the usual way via fractional linear transformations, where Q is exponential of 2 pi I tau, as we usually write in any study of modular forms and modular objects. So here in world of vertex algebras, what we're going to find is that these characters indeed are modular, namely they form a vector valued modular form. So there is a set of them labeled by lambda, and they'll be permuted one into another or linear combinations via this action on tau through S&T matrices. And these S&T matrices are precisely the ones which we saw in the world of MTC. So this arrow between modular tensor categories and vertex separator algebras is precisely encoding how modular group acts on characters of vertex separator algebra. So for instance, if you take so-called WZW model, that's a particular vertex separator algebra built out of group G. Here I'm using G as a compact Lie group. We can assume it to be simple and semi-simple. K is an integer called level, and for every such pair, you can form a vertex separator algebra, and if you ask how its characters transform, it will basically tell you S&T matrices of category, which is called Verlinde category. So I'm explaining yet another name from my title. So it involves Verlinde formula, and Verlinde category will also appear a couple of times in what I'm going to tell you. Now, this relation between vertex algebras and MTCs is kind of very algebraic, so it has nothing to do with the other link, topology, or so it seems. But the ingenious insight of Eric Verlinde was that you can also use this S&T matrices, which is all about Q-series, modular transformations, and so on, to say something about what the corresponding topological field theories on three manifolds attached to this modular tensor categories should look like. Namely, he tells us that if you want to compute invariant, that this TQFT should assign to a very special three manifold, namely a circle cross Riemann times Riemann surface of genus G, then if you take matrix elements of this S matrix and perform the sum, so these particular elements are sometimes called conformal dimensions, you actually get the invariant of this three manifold. So, and it's always going to be an integer, because what it's trying to compute from the viewpoint of topological field theory is basically dimension of the Hilbert space, or maybe super dimension, that this TQFT associates to Riemann surface of genus G. So remember that in the standard IC axioms, which apply in the case I'm discussing, TQFT is a functor. It's a machine that associates numbers to three manifolds, vector spaces to surfaces of genus G, and categories to manifolds of codimension 2. In three-dimensional setting, codimension 2 means that it's collection of circles. And this MTC is precisely the category that such three-dimensional TQFT should associate to a circle. And the Hilbert space that it should associate to genus G Riemann surface has dimension given by this Verlinde formula. So that's one of the key formulas in this whole talk. So any questions so far?
But this is quantum dimension, right?
Well, there are two dimensions hidden on the slide or present in the slide. One is matrix elements as 0 lambda. So these are called quantum dimensions of simple objects lambda. So lambda, if we use the language of MTC, correspond to simple objects, and as 0 lambda are their quantum dimensions. But what this formula computes, it computes actual dimension of a vector space that TQFT assigns to genus G Riemann surface. So that's just normal dimension. It's a finite dimensional space, and its dimension is just a number. So in particular, Verlinde formula says that this combo is an integer, and that's actually non-obvious. For example, if you look at this S matrix, it has algebraic numbers as entries, and Verlinde says that not only in this example, but in any example, if you form the sum, the result is always going to be an integer. So that's another kind of neat, cute number theoretic aspect of it. So one dimension is quantum, but this dimension is purely standard classical dimension. Now, it's not a surprise that algebraic structures help us understand problems in topology. In particular, they usually encode in the algebraic setting a definition of topological quantum field theory. For example, one fact, which is very popular, and until recently I even forgot the reference for it. So I would just state as a folklore theorem that given a Frobenius algebra, you always get a two-dimensional TQFT attached to it simply by thinking about product in a Frobenius algebra as something that TQFT should associate to pair of pens. Because if you think about TQFT as a functor in two-dimensional setting, everything comes from or is built from pairs of pens. So if you have two circles and then cobordism into a single circle, that's precisely the map from two copies of a vector space that two-dimensional TQFT should associate to codimension 1 manifold, namely a circle, into one copy of V. So from V tensor V to V, you get exactly the product. And recently I came across a reference, which of course then rang a bell, that this is described in a paper of Robert Dijkgraaf from late 80s or early 90s, I forget. And that's, of course, one of the references where you can find it. Likewise, in a three-dimensional setting, TQFTs that live on three manifolds with boundaries and then higher codimension sets are labeled by modular tensor categories. That's precisely the meaning of more explanation of this arrow here. In this case, it's a much harder theorem and is due to Turaev, who says that if you apply Turaev-Reshetikhin construction in a more general setting of modular tensor categories, you're always going to get three-dimensional TQFT, which again should associate numbers to three manifolds, vector spaces to surfaces of codimension 1, and categories to objects of codimension 2. But again, these are just circles, and to circle you associate exactly this MTC. So what about then invariance of three manifolds? So it turns out that the data of MTC again is sufficient, and there are many neat formulas, very explicit concrete formulas like the one shown here, that allow you to say, given a presentation of your three manifold, what the invariant should be. So all three manifolds can be built by surgeries on knots and links. So here is an illustration where I build a three manifold out of a bunch of circles, unknotted circles, by performing surgeries with various coefficients called here AI. So this data can be neatly encoded in some graph whose vertices are labeled by integers, and claim is that if you really care about invariant that TQFT should associate to this particular three manifold, it's maybe pretty complicated, then you have a very concrete combinatorial formula here where you take sums over the lambdas and put various matrix elements of this S matrix and T matrix and suitable combinations, where the weights in this kind of statistical sum, think about this as a statistical model that lives on this graph, is over products of vertices and edges. So there is something that's weight of the vertex, something that's weight of the edge in this statistical model, and the result is going to be the corresponding three manifold invariant. Again, details of this formula are not important. What's important is that there is a machine encoded in this general theorem that says that for any three manifold, you can produce an invariant, and it is in fact a topological invariant. So that's another reason why modular tensor categories are interesting, and this modular data plays a key role. So in particular, if you think about this Verlinde formula, it has exactly this structure. It's sum over lambda, and then this S0 lambda to the 2 minus 2g is actually a special case of this formula. Okay, I'll give another motivation for modular tensor categories. Like I promised, it will be fairly long motivation, and this is probably the last part of my motivation before I start telling you the solution, why we care about MTCs and what kind of questions we would like to address by this, why do we care about this dictionary to geometry. So let's start with the quantum group. In this case, quantum group for SL2, but anything I'm going to say will generalize to other quantum groups or other Cortan types and their close variants. At some point when with Witten we were working on geometric Langlands program, I was talking a lot to Edward Frankel. And at that point, I knew very little of representation theory. I still know very little. And Edward told me that if you're lost in a seminar on representation theory, always ask a question, what about SL2? Or how does it look for SL2? And that's being my to-go question in every representation theory seminar. So here is the quantum group for SL2. It's defined by generators EF and K, the usual Chevalier generators, and some relations that involve Q. That's why it's quantum group. And what we're going to do, we'll set Q to be even root of unity. So it's root of order primitive, root of order 2 times P. And this is a little bit different from what is usually studied in the case of so-called small quantum groups, where one is trying to set Q to odd root of unity most of the time, but you can actually set it to even. There is nothing wrong with that. And those of you who heard nice talk by Pavel Ettingov earlier this week, in his talk, he actually talked about small quantum groups. So what we're going to consider is a close cousin called restricted quantum group, because relations are slightly different. But the idea is very similar. So we'll take even root of unity. We'll impose additional relations that e to the p, e and f are nilpotent of order p. K becomes unipotent. So k to the 2p is equal to identity. And you can quickly check that indeed this is very compatible with these relations. For example, if q is root of unity of order 2p, then repeating this operation, namely conjugating either e or f by k, should indeed give me q to the 2p after repeating it p times. And if q to the 2p is identity, then this is definitely consistent to set k to the 2p is 1 and so on. So
is p prime? Or doesn't have to be?
P doesn't have to be prime. So actually P can be anything here.
Thank you.
Yeah, sorry, the notation doesn't mean to suggest it's prime. And like I say, it's a good question to ask what happens. There should be analog of this story I'm gonna tell you, but I don't know the answer, if P is odd root of unity as well. But what I'm gonna tell you next is something that I don't know how to phrase in that case. So dividing by these additional relations gives you a quotient, which is very nice. It's an algebra, in fact, of finite dimension. It's dimension 2 times p cubed. So the numbers 2 and, yeah, so some numbers here are not random. So for example, 3 is the dimension for SL2. So if I repeat this procedure for other groups, what I'll get is basically p to the dimension of my Lie algebra, underlying Lie algebra, and there will be 2 to the power rank. So rank of SL2 is 1, so that's why it's 2 to the first power. So this algebra also has a finite dimensional center. That's maybe less surprising, and but it's still interesting. It's of dimension 3p minus 1, at least for SL2. So this is basic information that we extracted from the previous slide. So we'll study this UQ bar. Bar means this notation restricted quantum group. So we obtained this fellow from quantum group by imposing additional relations, which are meaningful at roots of unity. And we get something of finite dimension, and it has a finite dimensional center. So now the statement is that on this finite dimensional center, you have a realization of SL2Z action. So SNT matrices that we already saw in several different contexts before, again, show up here. And previously, in my previous examples, I showed you already 2 examples of modular tensor categories, namely Fibonacci MTC. This was one example. Then I gave you Verlinde MTC, and I'm about to show you yet another example of MTC, which is a little bit more interesting and goes in yet another direction, and then it will kind of give an idea of what we expect on the MTC side. So this quantum group, a general value of Q, can be, first of all, specialized to root of unity. That's what we did. And then you find 3p minus 1 dimensional representation of SL2Z on its center. But then what's more popular, this is not so as well known as the statement that quantum group invariants of 3 manifolds, namely quantum groups at roots of unity, give you ways to produce quantum group invariants of 3 manifolds. And that's much more known. That's actually related to this Verlinde MTC that we discussed before. But this is something that's obtained from what we just constructed by applying additional operations. So it's a 2-step construction. And the Verlinde representation is much smaller. In this case, it would be of dimension p minus 1. It actually sits inside this one. So this one corresponds to non-semisimple modular tensor category. And this one is a semisimple modular tensor category. So Verlinde representation is a semisimple one. So corresponding vertex operator algebras are also interesting. This WZW model is a very standard VOA. It obeys the usual axioms, whereas the one which corresponds to this fellow, which we found just by setting Q to root of unity, is actually quite exotic vertex algebra. It's called logarithmic VOA. And the study of such logarithmic vertex algebras and the corresponding non-semisimple modular tensor categories is exciting, cutting-edge kind of development that's still going on. There is a lot to be said, and I think we're just beginning to explore the rich world of these non-semisimple modular tensor categories. So recently, this 2-step construction and relation between both representations of SL2Z were given physics interpretation in this paper, and it will play a role in some application very much further down the road if I get time to get to that application.
But don't you kill something in the first step because you get something infinite dimensional?
Yes, that's what I briefly said here, that this restricted quantum group is a quotient of what you get from these relations at Q, namely you kill this e to the p, you impose e to the p is nilpotent, and k is unipotent.
All right, okay. Yeah.
Any other questions? Right.
Can you say a little more on how SL2Z acts on the center?
In this particular case, it acts in the following way. There is a representation of SL2Z of dimension p plus 1. So it's actually decomposing into several pieces. So one piece is of dimension p plus 1, and then plus, O plus, C2 or times representation of dimension p-1, and this p-1 is precisely the Verlinde representation, and it's tensored with the standard two-dimensional representation of SL2Z. So in this case, it splits into several pieces, but the structure that you asked about is actually getting very interesting and is not known in general for general group G. So that's a pretty cool question. Yeah, in fact, I should also add before I move on maybe, or I was planning to say it on the next slide actually, that the reason we care about non-semi-simple MTCs is that even usual modular tensor categories are not classified. But non-semi-simple MTCs is a much richer world, and taming that world is, in some sense, even more exciting or challenging, depending whether you want to look at the glass of half full or half empty. So, right, so they contain not just everything decomposes not just in direct sum of simple objects, but you have interesting extensions, projective modules. So that's what makes the story really rich and interesting. So to give a more refined answer to the previous question, therefore, here is our diagram back again. We'll consider correspondence between geometries of hyperkähler manifolds and modular tensor categories, but I'll care about variants of modular tensor categories, not just the strict rigorous definition of MTC as a non-degenerate spherical braided fusion category, but rather relaxing some of the conditions in this definition. Dropping some of the adjectives, for example, the previous slide showed you that working with non-semi-simple version of MTC is also something of interest. It still has connections to TQFTs and logarithmic VOAs, which are much less studied, but much more interesting, and that's actually what we are after. So this is, again, this discussion of both sides. So now I'll come back to original correspondence and try to flesh it out. And first of all, I want to say, what's the actual problem and why do we believe that there is a correspondence like this? So I don't have a full answer for how it should work, how to construct MTC directly out of X. That's the goal. But at this point, you may naturally ask, hey, Sergei, why do you even think that this is a reasonable question? It would be cool, of course, to have MTCs attached to nice hyperkähler geometries like Hilbert schemes or T star of CP1, but why do you think this is a reasonable question? Well, once I explain that MTC is pretty much the same information as TQFT or equivalently representation category of a vertex algebra, I can give the following answer. There is a way to go between geometry and TQFT proposed by Rosansky and Witten. So they say that if you have a hyperkähler manifold, you can attach to it a three-dimensional TQFT. So that's basically what the title of their paper says, and the paper is from 23 years ago. Shortly after, there was a work of Maxim Kontsevich and Misha Kapranov, who developed two parallel approaches to mathematical definition of this invariance of this TQFT-like constructions. Again, the starting point is geometry of the space X. It may be a Coulomb branch of some 3D n equals 4 theory. It doesn't have to be a Coulomb branch. It may be K3. In this case, again, it's totally fine to have compact hyperkähler manifold, which can never be realized as a Coulomb branch. So again, our setting is fairly general. And these people tell us that there is a three-dimensional TQFT. So then the natural question is, what is the MTC underlying this TQFT? So I just told you that MTC data and TQFT data are very similarly related. So I should have no trouble extracting MTC from their construction, right? Well, so many people thought, and including Justin Roberts and Willerton, who tried to ask exactly this question. In the original paper, Rosansky Witten described in great detail what this TQFT, or invariance to be more precise, of closed three manifolds and surfaces of codimension 2 are. So they tell you the Hilbert space in this three-dimensional theory, and they tell you numerical invariance. But they didn't look at the categories, which is a natural question. And then some people try to fill this gap, basically. And based on mathematical developments, which I mentioned a moment ago, namely by Kontsevich and Kapranov, you quickly come to the answer that the category that's attached to a space X, to this geometry, is one of the first ones you would think of. So when I started my talk, you could have said, hey, let's take for the category just derived category of coherent sheaves. That's something that you all always attach to geometric space. If you have hyperkähler geometry, it's even more than what you need as far as the structure goes to define derived category of coherent sheaves. So that's already a natural object, and that's precisely what appears here in the Rozansky-Witten setting. But then comes an interesting question that derived category of coherent sheaves on X is a very natural geometric answer. But question is, does it carry all the structure that we expect from modular tensor category? In particular, what is S and T matrices? And if I give you, for example, K3 or T star of CP1, where is the SL2Z action? So it should be basically SL2Z action on the Grothendieck group of this category. Is it obvious? And if so, what are the S and T matrices? So this is precisely the actual question we're trying to approach. If X is compact, Rozansky and Witten, in fact, gave a full enough description of the problem so that this SL2Z action is indeed present and can be extracted from geometry. But it becomes more interesting when X is non-compact. Then it's absolutely unclear, and that's precisely what we're trying to approach. And that's exactly where deviations from standard modular tensor categories will start appearing. For example, that's the world in which you'll see some of the non-semi-simple MTCs. So let me go now to formulation or fully decode all the words in a title. So I explained what Coulomb branches are. These are particular examples that you can take for geometry of space X. So I already showed you Verlinde formula. Here it is again on a slide. Verlinde formula basically says how to compute dimension of the Hilbert space in 3D2Q of T via the data of S and T matrices. So namely, as appears here, its matrix elements. And the problem that we want to consider, again, motivated by this discussion, is when the Hilbert space is actually infinite dimensional. This will be the case for Rozansky-Witten theory and many other close cousins of this theory when X is non-compact. So that's when things become interesting. So in that case, when Hilbert space is infinite dimensional, when X is non-compact, formally this will be meaningless quantity. So it will be either infinity or need some regularization. So question is, what do you do? Well, the idea that was in mathematical physics popularized by Muru, Nekrasov, and Shatashvili, who skillfully apply this to many other problems, and the context that I'll describe to you is closer to these works, is that if your Hilbert space is infinite dimensional, but has a grading, then you can basically consider the graded dimension of this Hilbert space. So it will be an expression of the form sum of the graded dimensions of the graded pieces with another variable that I'm going to call t to the nth power. So for nth graded piece, there will be t to the n. So here n is just usual z grading. And in the setting that we're going to consider, there is this z grading for the t variable will come from circle action on space X. So therefore, if you want to work with X, which is non-compact, but is comes equipped with a circle action, then you can claim is that you can fix this problem, and you can consider this equivariant with respect to the circle action version of the Verlinde formula, and that's the name. The equivariant Verlinde formula will stand for this equivariant version. And the beauty of this story will be that even though what we're trying to describe is associated with infinite dimensional Hilbert spaces, from the viewpoint of topology, the sum here will be very much like in the previous case, namely running over finite set of lambdas. So even though the whole object, or if you wish, MTC associated to the setting has infinitely many simple objects, it will effectively behave as the usual one with a finite set. So that's the important point. That summation here over lambda will be finite, and it will effectively behave as something with finitely many simple objects. So that's the name. So to implement it, again, you just have to apply this equivariant perspective to non-compact spaces X. And in recent work with this gentleman, so maybe I'm not sure if I can try to move it. Oops, I think I just made it a little worse. Yeah, with this gentleman, we basically give a very concrete formula. So if you have, if you're interested to know what is the S and T matrices associated to space X, which would be Coulomb branch or could be something more general, if fixed points are isolated, there is a very concrete formula which expresses matrix elements of T and S in terms of various equivariant characteristic classes at the fixed point. For example, if you have an isolated fixed point and the circle action acts on normal bundle to this fixed point with some weights, W1, W2, and it could be multidimensional. And if it has moment map mu, then this data basically goes into the definition of S and T matrices. So, right. Then, in particular, we applied one of the examples that we considered was a case when X is a particular Coulomb branch. It has two fixed points. And again, you can compute this data of geometric data on the geometry side, how circle action acts on the Coulomb branch. And from this, you reproduce a Fibonacci MTC as one of the answers. So claim is that Rosansky-Witten theory with that particular Coulomb branch should be computing the invariance of three manifolds and other manifolds as Fibonacci MTC. So in that case, the fixed points are isolated and so on. So that's right. So conceptually, for perhaps mathematical physicists or those of you who are interested in physics, I'm not going to describe in detail what that X was. I just said that it's particular space, and you can find it in the paper. But it came from some four-dimensional theory, in fact, of type that Donaldson and Witten studied. It's a so-called Witten twist of Argyris-Douglas theory. And if you consider this theory on a circle cross M3, you can basically think about what happens when you start doing cutting and gluing along M3. Then what you're describing is some effective TQFT on a three manifold. And that Fibonacci category I just showed you is what this TQFT associates to a circle. So again, think about this dictionary between geometry and algebra. So what we're finding is that given a Coulomb branch of three-dimensional n equals 4 theory, that in this case comes from even higher dimensions, you get standard category. Let's see, I'm gonna skip this slide. And I just want to show that these examples can be generalized in many ways. So particular space that we took in that paper was an example of moduli space of Higgs bundles with so-called wild ramification. That's one of the ways of constructing hyperkähler manifolds. It had two fixed points, but it was heavily based on work of these young people, all of whom are wonderful, who studied moduli spaces of Higgs bundles with wild ramification and gave lots of other examples. So here is the geometry of set to which this moduli space is non-compact X contracts and has, in this case, three fixed points, 1, 2, and 3. In this case, 4 fixed points, and so on. And in these examples, S and T matrices would be of size 3, size 4, and so on. So then I'll probably show you just one more example in view of time. So this is an example where fixed points are not isolated, and in fact, historically, it was developed first. So this is a case where X is a particular quotient of a joint representation of UN plus k copies of n-dimensional fundamental representation, on which U1 symmetry acts by weight 1 action on the adjoint. So it's a concrete space, and it also comes as a space of solutions to some PTEs, namely it's called vortex moduli space. And you can ask what kind of TQFT or what kind of modular tensor category you get in this setting. So if you think about this equivariant Verlinde formula, which describes, which basically attaches, which is a TQFT that depends on T on the Riemann surface of genus G, all you have to know is Frobenius algebra, namely you have to know the product or what to associate to a pair of pens. And this problem for this space X reduces to the following expression for the structure constants. So if you are working with, so if you denote lambdas, your states, then they can run from 0 up to k. So k enters into this problem as such. And the structure constants take value either 1 if you're inside of this tetrahedron inscribed inside the cube of size k, or they take value t to the distance to this cube, where t is our equivariant parameter and delta lambda is the distance from some point labeled by lambda 1, lambda 2, lambda 3 to that cube. So some of you probably already recognize a familiar structure, in part because if you think about the space and take t to be 0, then you essentially remove this adjoint piece. In that case, what I give to you is a Keller quotient construction of the Grossmanian. And if you think about the relation between cohomology of Grossmanian and the Verlinde algebra found by Witten, then what we're doing basically is a deformation of that story. So in particular, we expect that if t goes to 0, we should get just cohomology or quantum cohomology or quantum K-theory of Grossmanian. And indeed, this structure constants I'm describing to you, if t goes to 0, are precisely the ones which you find in quantum cohomology or K-theory of the corresponding Grossmanian. But now with the t variable, it's slightly more general. And if you want to use this structure constants to compute the partition function on a genus 2 Riemann surface, what you get is a series in t, in this variable t, such that each coefficient of every power of t is a cubic polynomial. So when t goes to 0, you only have this first line in the expression, and that's in fact the usual Verlinde formula in this case for SL2 at level k. So that's indeed what we should expect from the relation to the Grossmanian. But turning on this equivariant parameter t gives you an infinite series which continues further and further down the road. So in other words, what this expression computes is the following. The statement is that what this TQFT or Frobenius algebra gives you, this equivariant Verlinde formula, is an integral over the moduli space of Higgs bundles, G Higgs bundles over genus G Riemann surface, equivariant with respect to circle action on the moduli space of Higgs bundles, which sometimes is called Hitchin's action. So another perspective on Verlinde formula that we saw several times before, but this is a new perspective that I didn't mention, is that what it computes is certain characteristic class integrated over the bond G, the moduli space of G bundles over Riemann surface sigma. And if M is compact, and namely if group is compact, group G is compact, there is no problem. This is just an integral, and it depends on K, the level. It depends on choice of the group G, and of course on the Riemann surface sigma. And computing this integral is challenging, but very doable problem. And you get a finite number, which is precisely this Verlinde formula, which can be also expressed in terms of S and T matrices. But the question here that this equivariant Verlinde formula addresses is what happens if you replace G bundles on sigma by complex GC. You complexify the group and you study GC bundles on sigma. This space is equivalent in one of the complex structures or holomorphic symplectic forms to moduli space of Higgs bundles, G Higgs bundles, and comes equipped with a circle action, which is precisely that circle action I mentioned earlier. It was found by Hitchin. So you can compute this sort of integral using equivariant localization. Yeah, so I think I'll probably stop here since I reached reasonable time limit. Thank you.
Okay, thank you very much. So let's thank Sergei for a wonderful talk. And if there are any questions, please. Yes, Anton.
You mentioned Hauser-Stennis something in the previous slide, but you can change the slide very quickly. What was
well, this formula was first predicted in physics and our work with Dupay, but again, because it was mathematical physics, it was not a rigorous proof. I should mention that then rigorous proofs came shortly after by Daniel Halper-Lessner and Tamas and Andras Chenes. I don't know if this is published actually. So they told me that they have a proof of this using residues. So that's one of the their favorite techniques. Yeah.
But they write the formula in a different way, maybe, or?
Yeah, so they that's right. Each of these proofs uses slightly different approach, slightly different technique, and theirs is using residues. So I'm not an expert on it, and in fact, like I said, I don't know if it's actually published, but I was told that they have a proof back when this was active area. Yeah.
Other questions?
Yeah, I have a question. So do you expect an analog of this last formula where instead of sort of Chern-Simons series with complex gauge group, you have perhaps Chern-Simons series with split real gauge group rather than the real compact form of the gauge group?
Yeah, then that's a great question. I don't know, to be honest, because so here and in many other places where we and other people managed to make sense of Chern-Simons theory where group is complex, there is always something like the circle action that helps a lot. And of course, we would lose that if we consider split real form.
Yeah.
There are finite groups which maybe can be used for localization analogous to this. We would, of course, lose parameter T, which is important. Yeah. But maybe something can be done. In fact, Anton is an expert on it, probably more than I
am. Simon, did you want to ask something?
So in the non-sim, to get a three-manifold invariant, the action of SL2Z is not enough, right? We need something like invariance with respect to the Kirby move, that different surgeries of the same manifold can give you the same answer. So in the non-semi-simple, is it possible to verify it, or?
Right. So I think there are two. Right. So there are two aspects to this question. One is even in a semi-simple case, the goal is to go beyond just numbers which are S and T matrices. So the statement is that there is an actual category attached to X, which can be Coulomb branch, could be something more general, and existence of such category, if X is compact, already follows from Rosansky and Witten. So question is to identify what this category is in setting when X is non-compact, like a Coulomb branch. So there should be a categorical data, and that's actually more interesting. So in physics, this would be called category of line operators, but that has not been studied, at least not in a way that is useful enough for computing invariance of three manifolds. So in some sense, I would say that not only one needs to, yeah. So to verify or study invariance of non-semi-simple TQFTs or logarithmic TQFTs on three manifolds, one really it's better to work with categories directly. So here, for the sake of presentation, I focused on modular data S and T matrices, just because that's a simpler aspect. But I don't want to de-emphasize that there is a category behind the scene, and in that work with Nakajima, Dupay, Kaye, and Kolle-Dedushenko, we actually focus on categories, and that's, I think, I would have to bring it back if I am to make a connection with non-semi-simple invariants. So that's playing an important role.
May I ask a naive question? So in the middle of your talk, you mentioned restricted quantum group at roots of unity. And does it have any connection to the last part about Coulomb branches?
Yes, it does. So this is the part for which I didn't have time. It would be my last example. That's what we're doing currently with these young people, and it can be found actually, interestingly, if you consider another hyperkähler manifold, which is roughly speaking moduli space of Higgs bundles, G Higgs bundles on a disk. So that's actually not only non-compact hyperkähler manifold, it's actually infinite dimensional. So it's a double whammy. We make our problem much worse. So, and in that setting, we find connection precisely with those non-semi-simple MTCs, which I mentioned in the previous talk. Oh, in the previous slides, in the middle of the discussion.
I also had one naive question. So you mentioned this the action of the modular group on the Grotner group of the category. There is a related construction with the modular function and an action of the mapping class group on the Hilbert space. So you can, if you take a torus, you get this SL2Z action on the Hilbert space. Are these two constructions related?
In which case? So torus and Hilbert space of what?
Well, so you can start with the I don't know, the braid monoidal category. Construct a modular puncture. Take construct it on a surface on which, like, you know, puncture torus. You get an SL2Z action on the Hilbert space that you attach to the surface.
You mentioned punctured torus. That was intentional. You want punctured torus, right?
Say I want punctured torus. Does somehow feed into this general logic of, you know, the SL2Z action on the Grotner group of some category, or it's just completely unrelated story?
Well, if you have a puncture, that's why I try to clarify. It's a little, it's a quite a bit more delicate. So yeah, because the torus without a puncture is basically what surrounds. It's a boundary of a tubular neighborhood of a circle. So in this T axioms, we associate category to a circle, and in 3D TQFT, it's surrounded by something whose boundary is the usual torus, and then mapping class group of that usual torus is SL2Z. So it is true that there is another SL2Z action if you have a punctured torus, but that object would be slightly more interesting and delicate in a sense. It doesn't come from just a circle. It comes from a circle which also has a line trying to go through, joining it. That's the puncture. And it is connected, so I don't want to say it's unrelated, but it's a little bit more delicate. So it fits into this framework, but yeah, in a slightly more subtle way.
Thank you. Anton?
I remember in the beginning you said that you had this picture where you have two-dimensional TQFTs and three-dimensional TQFTs, but then and for both of them you had this Verlinde and then Turaev, I don't know, and then for four-dimensional you don't have any mathematical picture, or you had Frobenius algebras for two-dimensional, then MTCs for three-dimensional. What's four-dimensional?
Yeah, that's a good question. But in some sense, it depends what we want, I guess. In some sense, we do. So T axioms give you a definition of TQFT in any dimension, but not fully extended, right? So the usual T's definition says it's a functor in the category of Bordisms, and you can associate numbers and vector space.
I understand. Maybe we don't know what we want, but
yeah, so if you ask about structures, algebraic structures underlined fully extended or extended pretty far in dimension 4, that's still going to be a functor in this spirit. But it's true, we don't know what's analog of modular tensor category or Frobenius algebra. The closest I can think of is what Jacob Lurie is studying. So I don't know how helpful it will be to understand actual invariance of three manifolds. That's not clear. But I want to emphasize that even in the even in this discussion, we had to deviate from standard MTCs very quickly. So many interesting invariants of three manifolds, such as, for example, Turaev torsion or Seiberg-Witten invariants, and many of their close cousins, they don't come from a traditional TQFT. They come from this non-semi-simple version, which is not developed at all. I mean, there are many papers, but we're just beginning to explore this rich, wonderful story. So it seems that invariants that we really care and need on topology, which are strong and distinguish a lot of powerful things, and hopefully this will be the case for invariants which detect smooth structures in dimension 4, they deviate from traditional T axioms, even at the first few levels.
So it's still not clear in which ways they should deviate in 4 dimensions.
It's not even clear in 3 dimensions. So why should it be any clearer in dimension 4? Yeah, that's right. I think if you want qualitative answer, that T's axioms and many of the related constructions, for example, of usual semi-simple MTCs that we mentioned, they assume finitely many simple objects. So finiteness is a crucial thing. That's what we're trying to fight in this discussion today with this equivariant version, or it comes from non-compactness. But the message from Seiberg-Witten invariants in dimension 3 and in dimension 4, as well as Donaldson invariants, is that those Hilbert spaces are never finite dimensional. If you study any interesting TQFT that comes from topological twist of, I don't know, Seiberg-Witten type theory and so on, these Coulomb branches, they're never compact. So Hilbert spaces are never finite dimensional. That's the general feature. That may be the main lesson, which is why already at the level of Hilbert spaces you get immediate problem. So.
By the way, by non-semi-simple, you mean that there can be infinitely many simple objects, but still no projectives?
No, actually, when we were discussing it back then, I meant that there are finitely many. So there are two problems, and I think both of them will be important in generalizations. I'm glad this came up now, because at that point we were discussing issue of having projectives which are not simple, namely indecomposables which are not irreducible, which are not reducible. But now we're discussing, and then this was also related to the talk, infinite set of simple objects, simple or projective. So in general, both of them definitely need to be accommodated. So yeah. So I would say to answer Anton's question, it has to be a generalization of whatever algebraic structure has to be, what we're looking for has to accommodate both of these things somehow.
Okay. Are there any more questions? If not, let's thank Sergei for the wonderful talk again.
Oh, thank you.
And next week there we'll have Siddhartha Sahi. So hope to see you there. Okay, thank you very much.
Thank you, Sasha. Thank you, guys.
Ну хорошо, спасибо еще раз.
Да, спасибо.
Вот, да. Сергей, если можно, ты можешь мне прислать слайды, действительно?
Слайды, хорошо.
Я бы тогда это просто выложил на сайт.
Ага, договорились, ладно, спасибо.
Ну ладно.
Я извиняюсь, что я с технологией не очень хорошо.
Нет, все отлично было, действительно.
Отлично,
очень здорово. Да. Ну ладно, все.
Ну хорошо, спасибо.
Спасибо. Ага. До свидания, счастливо.